So today we're doing a deep dive based on some notes from Andrea Mignini, and he calls it a vertiginous territory. We're talking about string theory.
Yeah, and it's vertiginous for a reason. I mean, what it's trying to do is solve probably the single greatest challenge in modern physics.
Which is that great divide, right? The fact that we have these two amazing theories of physics that they don't talk to each other.
Exactly. You've got Einstein's general relativity for the big stuff stars, galaxies. It works perfectly. And then you have quantum mechanics for the infinitely small.
But try to use them together, say, on something like a black hole.
And the math just goes crazy. You get nonsense answers, infinities. It completely breaks down.
So this is where string theory comes in, with a proposal that at first sounds, Mini used the word folly, crazy.
It does. It says, what if everything we see, an electron, a quark, any particle, what if it isn't a tiny little point? What if it's a minuscule vibrating loop of string?
And this is where that beautiful analogy comes from, right? The cosmic symphony.
That's the one. It's the idea that every particle is just a different note played on the same fundamental string.
So one vibration gives you a photon.
And a different vibration gives you an electron. They're all just expressions of the same one thing.
But the really magical part, the thing that made physicists sit up and pay attention, was gravity.
Yes, this is the key. When you work through the math of how these strings can vibrate, one particular vibration, one note, it pops out. And it has the exact properties of the graviton.
The hypothetical particle of gravity. So it wasn't something they had to add in.
Not at all. It was a natural consequence. In our current standard model, gravity is sort of bolted on the side. In string theory, it's part of the package from the very beginning. It's just there.
Okay, something that elegant has to have a catch. And I know there's a big one.
Oh, it's a huge one. For the math to work, for it to be consistent, the universe can't just have the 4 dimensions we know and love.
You mean our 3 of space and 1 of time?
Right. The equations demand 10 dimensions.
And, okay, so where are the other 6?
The hypothesis is that they're rolled up on themselves. They're compacted down to a scale so incredibly tiny we could never hope to see them.
The garden hose analogy.
Exactly. From a mile away, a hose is just a one-dimensional line. But when you get up close,
you see its circumference, the second dimension.
Right. So the idea is that space itself has these tiny, curled-up dimensions everywhere.
And this whole theory, it had a kind of messy start, didn't it? It popped up in the 60s, then exploded in the 80s, but then they found, 5 different versions of it?
Chaos. It was a crisis. 5 competing theories. Until 1995, when Edward Witten proposed they were all just different views of the same deeper thing.
M theory.
M theory, which, just to add to the fun, requires 11 dimensions.
Of course it does.
Yeah.
So this all leads to the big question, the one we have to ask. Does it actually work? Is there any experimental proof?
And the honest answer right now is no.
Nothing.
Nothing direct. The kind of energy you would need to actually see a string vibrate is it's astronomical. So far beyond what even the Large Hadron Collider at CERN can do.
So is the theory dead?
I wouldn't say dead. Maney calls it a fervent laboratory of ideas, and I think that's perfect. It might not be the final answer, but the mathematical tools it's given physicists.
They're being used in other fields.
All over the place, yeah. It opened up doors in mathematics people didn't even know were there.
So we're left with this kind of poetic vision. The universe is this pure symphony where everything from matter to the forces like gravity is just music.
It's an incredibly compelling and consistent picture, even if we can't quite access it yet.
Which maybe leaves you with the real question. It might not be about whether string theory is ultimately right or wrong.
No. The question is, which pieces of this magnificent kind of crazy construction will survive to become part of the next great revolution in physics? That's the real mystery.